Vibrodiagnostics of the smart mechatronic applications. Training video within Emoco 4.E project. Vibrodiagnostics is an important engineering area. It uses mechanical manifestations measurement and analysis to evaluate the machine health, which is necessary for long and safe life of the mechatronic applications, mainly the machines. In the industrial practice, mainly the machines with rotational movement are measured, analyzed, and diagnosed. Vibrodiagnostic is a subpart of the technical diagnostic, which includes, for example, tribology, thermal diagnostic, sound diagnostic, and many others. It is a non-destructive type of diagnostics as well as non-dismantling method performed in the place of installation of the machine. This is very beneficial, because the diagnosed machine cannot be turned down, disassembled and transferred to the place where the diagnostic can be performed. Vibration-based diagnostic can save manufacturing and financial losses thanks to the early fault detection. For the vibrodiagnostics, mechanical movement of the vibrating surface is measured. To do this, contact or non-contact sensors can be used. Movement, and also vibrations, can be described by one of the following quantities. Displacement of the vibrations, represented by the distance of the moving mass point. Vibration velocity, representing a speed of the moving mass point, and finally vibration acceleration, which describes the acceleration of the moving mass point. The type of measured quantity, as described above, depends on the machine type, standard for the particular machine, expected frequency range of the signal and the fault type to be diagnosed, and finally also on the knowledge and experience of the user. In the practical industrial environment, the rotating machines are exclusively diagnosed. From this reason, measured, processed and diagnosed quantities are periodic and harmonic.
Sensors used in the vibrodiagnostic. Accelerometers, sensors measuring input mechanical vibrations and providing the user electrical signal, mainly voltage or current, proportional to the measured acceleration, are one of the most used sensor in the industrial vibrodiagnostics. In the top part of the screen, standard industrial piezoelectric accelerometers can be seen. They are always in the metal housing with appropriate IP rating against dust, water or moisture. Thanks to the robust housing, they can be directly mounted onto the machine to be diagnosed. They have an industrial connector, and the signal sourcing from the accelerometer represents input acceleration as current loop, or as an electric charge. In the bottom part, the MEMS, micro-electromechanical systems, devices can be seen. These, relatively modern and prospective electronic components, are intended to be built in the electric circuit, on a printed circuit board. They need the additional electronic components for their successful function and ongoing signal processing. Their advantage is in the low price, small size, and also in the sufficient noise parameters compared to the standard piezoelectric accelerometers. Eddy current sensors, which are used to measure the displacement of a vibrations, uses eddy current principle. From this reason, they must measure the distance only from the electrically conductive material, where eddy currents can be initiated. Typical range for distance measurement is from 2 mm up to 16 mm, and the sensitivity is, except the other conditions, dependent on the material of the sensed object. Typical displacement sensors can be seen in the top part of the screen. In the bottom part, passive electrodynamic sensors are shown. They are based on the principle of moving permanent magnet in the wired coil and induction of the voltage dependent on the speed of moving, which is proportional to the vibrations affecting the sensor. The sensors have relatively high dimensions, compared to the accelerometers and eddy current sensors, and due to the mechanical principle of measurement, they also have relatively low high limit frequency. From this reason, they are used mainly for low-speed machines, where the generated and measured frequencies are relatively low. This type of sensors is also used as a geophones for measurement of the earthquake as well as other geological phenomena.
Except of the vibrations, other quantities are measured as well. One of the most important quantity in vibrodiagnostics are the revolutions of a machine. Revolutions are measured exclusively using non-contact methods, using optical or magnetic sensors. A special measuring wheel containing defined number of teeth is rigidly connected to the measurement shaft, and the magnetic sensor is, let's say, counting the metal teeth. Another group of measurement sensors or equipment are the laser vibrometers. They are quite expensive, but very precise and have a high accuracy. These sensors are mainly used in the laboratories during scientific experiments, for on-demand diagnostic, or in the applications where using of the standard sensors could be expensive or problematic or even impossible. A big advantage is that you cannot prepare the place for any standard sensor, like drilling the hole, creating a thread, mounting or gluing the sensor, prepare cabling and the measuring unit. A user simply turns the laser on, focuses the beam to the measured surface, and executes the measurement. Now let's have a look on the machine state evaluation and analysis. Evaluation of the machine state tells the user about the state of a machine, often called machine health. But it tells the user nothing about the root cause of the problem to be able to solve or repair it. On the other hand, machine state analysis analyzes the vibration signal, and the procedure is trying to find the root cause of the problem. So, the machine state evaluation only announces that there is a problem thanks to increased vibrations. This process is covered by the international standards dependent of the machine size, type, power, using etc. Very often only the single value condition indicators are calculated and provided to the user. One of the most used is RMS value of the vibration velocity, measured in the frequency range from 1 Hz to 1 kHz. This is frequently called as ISO vibration velocity value and is based in the ISO 2816 International ISO standard. For any machine, the user can find the appropriate standard. In the bottom part of the screen, you can see the examples of the standards for radial or axial industrial fans, machining center, or the well-known API standard, used mainly for the machines with the sleeve journal bearings, used in the United States. As it has been previously mentioned, machine state analysis is trying to find the root cause of the faulty state of a machine. Unfortunately, most of these procedures are not covered by a standard, and the procedures are from the high part experience-based. For machine state evaluation, advanced condition indicators calculation is mostly used. One of the important type is trending of the data. Trend is a historical record of a quantity, and it does not depend if a quantity is a single number, like ISO vibration velocity or temperature, or the complete frequency spectrum of a signal. It is recommended to trend all possible values, because the user does not know which value will be beneficial in the future. Very helpful type of the analysis is the analysis of a spectral components in the signal. Spectrum gives very clear insight into the frequency parameters and components of a signal and is very often calculated using FFT algorithm. There are also another analysis that takes a significant place in the vibrodiagnostics, like cepstral analysis, CPB spectrum, which states for constant percentage band, different types of weighted and filtered spectra, short-time Fourier transform spectrum, waterfall charts, and many others. Thanks to the knowledge of the parameters of a machine, failures of the machine as well as its manifestations in the spectral domain, user is able to distinguish about the possible fault of a machine based only on the frequency analysis and frequency components of the signal. Vibration measurement is always good to be relative. Since there are given limits for the machine in some standards, each machine is different. There doesn't exist two same machines, even if they are manufactured as the same type. Their vibration behavior is strongly dependent on the surrounding conditions, mainly the base quality, mounting features, surroundings, noise floor generated by the neighboring facilities, and also state of wear of the components. From this reason, it is always better to compare the current values with the historical data stored in the trends, than to check the current values with almost no historical knowledge. This decision process is very dependent on the previous knowledge and experience of the technical personnel. In the bottom part of the screen, a bathtub curve can be seen. This curve defines a life cycle of almost all processes worldwide. There are three main stages of the bathtub curve. Section 1, showing the initialization process of the machine after setup and commissioning. This section lasts the shortest time of the complete bathtub. As soon as the machine is established, standard operation takes place. This curve, shown as a part 2 on the chart, lasts the longest time. In the real condition, this time can last for the years. As soon as some component in the machine starts to be faulty, section 3 of the curve occurs. This section has a linear trend at the beginning, but exponential increase at the end of the chart. This is the last stage of the machine lifecycle, where the machine needs a repair or replacement of the component or a whole machine. It is good to mention that all the machines have the same behavior defined by this curve. In this particular case, machine health can be imagined as a quantity on the y-axis. But also, a price of the spare part can be placed there. The part is very expensive at the beginning of the component lifecycle, because it is pretty new and not so many components are manufactured yet. In the operating period, a lot of spare parts is produced, and the stocks are full of them, so the price is low, and at the end of the machine lifecycle, there is a lack of the component at the market, so the price is relatively high. This trend can also be expressed by this bathtub curve. A list of the most common machine faults is shown on this slide. Rotor unbalance as a main and the most typical fault is mentioned on the first place. In practice, a combined type of static and dynamic unbalance takes place, and this type of fault can be fixed by the balancing process. Misalignment of the clutch is caused by the non-ideal plane of the motor, as a propulsion and load. This misalignment can be parallel or in angle, but in the practice, combined misalignment often occurs. The misalignment can also be caused by the thermal expansion due to the different temperatures on the side of the propulsion and a load. Another, very common failure, is rolling element bearing fault. This type of fault has several stages of severity, and there exists a lot of methods how to diagnose it. It can be said that almost each world-famous manufacturer of the Vibrodiagnostic instruments has its own developed method for the bearing diagnostics. Similar situation is with the diagnostics of a gearbox and gear wheels wear. Another faults, like bent shaft, resonance of a system, pulley wear or mechanical looseness are relatively specific and not so commonly occurring faults. It is good to be said that there exists a lot of another mechanical faults, which are not listed in this slide, and which are also specific to the particular machines. What are the consequences when the machine failure occurs? As a first symptom, operational vibrations are increased. This is the main and most important issue. Another aspects are only the consequences of increased vibrations.
An aspect, which comes in hand with the increased vibrations, is increased audible noise. In short, the damaged machine is louder than the healthy one. If there is a fault, mechanical power or productivity of a machine is decreased. For example, a turbine generates less electricity, a mechanical press has not enough power, etc. In addition, manufacturing quality can also be decreased. For example, a CNC machine with damaged tool creates not precise specimens compared to the healthy machining tool. The machine, in increased wear, consumes more power from the grid and produces more heat compared to the healthy state. due to malfunction of any component, increased wear of bearings, fan components, belts or pulleys take place as well. In case of the machine failure, the lifetime of the machine is shortened, which leads to more frequent or unplanned stops, leading to the unpredictable costs for the repairs and, in fact, stop of the machine or of the overall technology, if a machine is a part of the crucial infrastructure. In case of the Vibrodiagnostics of an elevator, two major parts are diagnosed. Firstly, diagnostics and the health and state of the mechanical components, such as propulsion, inverter, gearbox, pulley, leading ropes, door malfunction, and so on. Second major part is a diagnostics of the overall cabin vibrations and exposure to the human standing of the ground inside the lift. This parameters correlates with the comfort of the passengers during the ride, and it is called as a ride quality in the standard. Diagnostics of the lift is also covered by the standards mentioned in this slide. On the right side you can see the typical ride profile of a lift cabin ride. A positive acceleration peak while the lift is departing, then the ride representing by no acceleration, and finally braking representing a negative peak in acceleration. The ride quality is according to the standard measured and evaluated in the specific regions of this typical lift acceleration ride profile to be comparative and generalized between several lift. The quantities, which are evaluated for the lift diagnostic, are following: vibration velocity in meters per second, vibration acceleration in meters per second squared, and acceleration jerk in meters per second cubed. Acceleration jerk can be imagined as a twitching or jerking of the acceleration. For the diagnostics of a lift, a special wireless vibration sensor has been designed, developed, and built. The sensor is a battery-powered device with magnetic adapter suitable for temporary or long-term monitoring of the vibrations of a lift. As it can be seen from the structure on the right side of the screen, sensor contains 3 MEMS accelerometers. ADXL 355 and ADXL 1002 for broadband vibration data acquisition in all 3 perpendicular axes and 1 low noise, and very low power accelerometer ADXL 367 for motion activation of the entire system. The heart of the sensor is the STM32WB55 microcontroller with wireless coprocessor allowing communication through a lot of wireless standards. BLE 5.0 as well as Wi-Fi is used as a communication interface with the supervised system. Since the sensor is battery-powered, also a lithium polymer rechargeable battery pack is installed inside the instrument. With the capacity of 200 mAh provides sufficient operating time for the sensor and for sufficient data acquisition. Charging of the batteries is ensured by the wireless charging standard QI, which is commonly used in almost all present small wireless devices. The smart wireless sensor is placed in the metal housing, which ensures high industrial-grade protection standard, possibility of precise and rough mounting to the measured place and, thanks to this, also tough mechanical coupling with the measured surface. On the right side an application in PC can be seen. This application receives the data from the sensor and display all the necessary parameters for the later diagnostic. The sensor render from the design stage can be seen on the left upper part of the screen. The internal printed circuit boards while charging can be seen in the middle picture, and finally a photo of the prototype of the sensor can be seen on the right side of the screen. As a proof of the measurement accuracy and suitability of the sensor design, a sample rides in the standard lift have been performed. The curve in the left bottom side of the screen represents the acceleration profile during the ride from the ground floor to the 3rd floor, through 3 floors. On the right graph, there can be seen the first integration of the measured acceleration, blue curve, representing the velocity of a lift. After the second integration of the input acceleration signal, the displacement curve, red color, is obtained. This graph represents the distance crossed by the lift and is equal to 3 floors with a height of 4 meters each. Instead of the traveled distance of a lift, the vibration manifestations of the lift cabin or lift propulsion can be measured and diagnosed. This brings us to the end of this presentation, and we would like to thank you for the attention.